First, to Nancy Rubins, Jaime Garza, and the Nancy Rubins studio for bringing this spectacular sculpture to our campus and making it possible for us to interact with this work every single day. And on top of that, taking out the time to really share your insights and your inspiration with us. We are really looking forward to this conversation and eager to learn more about your craft and your insights. I'd also like to thank Sharon Wood, Tricia Clayton, and the Cockrell School of Engineering because you are bringing incredible expertise about structural engineering to this conversation that really exceeds our own understanding at Landmarks. Several years ago, when we installed the piece, that's when we began getting questions about the aspects of how this piece was engineered. And that was the beginning point where we began imagining the possibility of a conversation so that we could share this expertise with our community because clearly it's a subject that surpasses our own knowledge. So we're really looking forward to this conversation and to learning from you. Last, I would like to thank the National Endowment for the Arts, the Texas Commission on the Arts, as well as the Stillwater Foundation. These entities support Landmarks generally, which allows us to be able to provide programs like this today. So again, thanks everyone for joining us, and I'm looking forward to our conversation. So I'll hand it over to Christine. Thanks.
Thanks, Andrée. So I'm going to begin by introducing our panelists. Since they're all very accomplished folks, I've included a long bio of the many accomplishments of each of them in the Facebook event. So please go ahead and read those there. For sake of time, I'll just share their name and their title, and they'll quickly say hello so you can recognize their face. So we have Tricia Clayton, who is an assistant professor in the Department of Civil, Architectural, and Environmental Engineering.
Hello.
We have Jaime Garza, who's principal at the Design Collaborative and the engineer on Monochrome for Austin.
Hi, everybody.
We have Nancy Rubins, the artist who created Monochrome for Austin.
Hello, everyone. Thanks for being here.
And we have Sharon Wood, who is the dean of the Cockrell School of Engineering at the University of Texas at Austin.
Hi, it's really a pleasure to be here. Thank you.
Great. So thank you everyone for joining us. We're going to start with a quick overview from Nancy Rubins on her inspiration and artistic process making the artwork. And then we're going to dive into the details of the engineering with Professor Clayton and Jaime Garza. And then we're going to open the conversation up to the full panel to have a larger conversation about the context of the work on campus and the relationships between art and engineering. And then finally, for the last 10 minutes of the conversation, we'll open it up to you to ask questions to the panelists. So if you have questions that you'd like to pose, please post them in the Facebook chat, and I will read them off at the end of our conversation and have our panelists answer them. Should you be tuning into this conversation after the Facebook Live event as a recording and you have more questions, please feel free to reach out to us at Landmarks. So with that, I'd like to invite Nancy Rubins to speak about the artwork.
Thank you so much, Christine. It's a pleasure to be here. Presently, this image we're looking at now is an overview of the sculpture that lives at UT Austin. Now, it's entitled Monochrome for Austin. And when I was first invited by Andrée Bober and Landmarks to come to Austin to see the site and to see the collection, I was truly impressed by the quality and the expanse of the collection there. And I was really honored to be invited to install the work for this site. You can go to the next slide, please. So Andrée offered me this fabulous site. This is the crossroads, roads that a bisection of roads between the humanities and the science buildings. And the building that the sculpture was to be in front of, is living in front of, is a beautiful and minimal building that seemed really like a good site for me to build a sculpture. I love that this site, I could build it so that people could walk under the sculpture to the door of the building, and it could also cantilever over into the street. And this drawing is a drawing that Jaime Garza made for me to show me where the manhole covers were, where the doors were, where we need to keep the sculpture a certain height off the ground. You can go to the next image, please. So this is a model of the structure that Jaime designed for me. Now, I've been working with Jaime Garza for close to 13 years now. And the first piece we did together was an extraordinarily large and complicated piece that was like a 95-foot cantilever that was about 75 feet tall, and it cantilevered over kind of this spaghetti canyon of roads. And like I said, it was very complex. And at that time, I'd been working with some very competent engineers who I liked. However, those engineers were only able to run the numbers and design a structure for me to bear the weight of the work that me and my crew were installing. And me and my crew have been building sculptures for many years without engineers, but in certain public situations, you need them. And I asked my engineer at that time, you know, you really make a good superstructure, but I need to be able to run the numbers on these elements and the structural aspect that me and my crew are adding to the piece. And my engineer at the time said, you know, we're structural and that's aeronautic. We don't do that. So when I started talking with Jaime, I said to her, you know, I really need an engineer to look at what me and my crew have been doing with these elements, look at this tensegrity, this kind of cockamamie tensegrity that we've developed for this work, and help us run the numbers on what these wires and the tension of these cables actually, what the numbers actually are, what the elements are actually able to hold. And Jaime was able to do that for me. And beyond that, she was able to say, you know, you need to have X amount of wires going from each element or more. And we, of course, usually did more. Or maybe when it's boat to boat or element to element, you use a bolt and washers here or there. So she started giving us suggestions and advice how to make more sound what we were doing, which was already relatively sound. Then I also said to her, you know, these pieces need to be flexible. Every time I install this piece, it's installed in a different configuration. And when I get to the site, sometimes I need to build an attenuation of a cantilever in a certain direction that I don't know about until I get there. So Jaime was able to design for me these things we call the T's, so that we were able to clamp these T-shaped structures onto either the 4x4 or a T to a T, so we could make these articulated attenuations. You can go to the next slide. This is the model of the study. So for this piece. Now, I call this a study. It's not really a model because the boats went in a very different way than the actual study has them. But I think that this is a gorgeous piece in itself. I really love, it's like a little sculpture in itself. Now, the scale of this is 1.5 inch equals a foot. And that is because these little model boats that my studio assistant made for me, plank by plank, are of that scale. So we just kept everything of that scale. So you can see, I believe this is the Raceway, the street with the purple line in the front, the door of the building, the university building behind it. You walk under the sculpture to the left to get to the door. You can keep moving through these images. This is from the building, the door of the building would be on the left. So we're working out basically scale and where the cantilever will go in these studies, in this study. And this is an overview of the piece once it's installed at the university. You can keep, yep. Now, Jaime and I, beyond the pieces, this monochrome series, and there were 4 of them. The first 2 had no plinth and went to Albright Knox Museum in Buffalo. And that was initially monochrome 1. And when Jaime designed these structures for me, I asked her to design them so that they could basically live anywhere. Because when they first went into the gallery, which is it's a large indoor space, for an outdoor space, it's small, the structure needed to be able to fit into the gallery and be installed relatively quickly. And the structure needed to be able to come apart and then live anywhere in the world. And after Jaime designed these structures, I said, Jaime, are these things really going to live anywhere? He said, yep, they can live anywhere. Maybe not on the top of Aspen Mountains, but definitely in Aspen. And I thought that that was truly beautiful that she could develop that for me. So the plinth evolved after I built the sister piece for this for the city of Paris at the University of Paris. And I worked with Parisian engineers and designers to design that plinth. And at that time, it was a steel structure with concrete and a stainless steel sheathing around the steel structure. I wasn't so happy with that plinth. So I said to Jaime, I really would like this plinth to be like a solid plates of stainless steel. And in my discussions with her, she said that there are something she calls stiffeners in there, and she can explain that better to you. But I was very happy with this plinth. I think the most elegant engineering that Jaime has ever done for me is our friend Fluid Metal, which is a piece made out of very dense aluminum spring animals, children's spring animals from the 50s and 60s and 70s that have been ripped out of playgrounds recently. And this piece is a 65-foot cantilever, and the cantilever is held in place through high-tension cables under compression, and it's just an exquisite piece. And most recently, Jaime's worked with me on the Diversifolia series, and it's really been a pleasure, Jaime, and I'm going to let you start talking now.
Thank you, Nancy. Tricia, you ready?
Yeah. Jaime, it is so great to get to talk to you and hear a little bit more about the structural design of this piece. So just like Nancy gave us a little bit of the overview of her vision and design of this piece, can you tell us a little bit about your involvement, your design process, and how you interacted with Nancy, the artist, throughout the design process?
Yes. And I don't know if this is the University of Texas's fault, but I always say, yes, we can do whatever. Whenever a client asks, can we do this? I'm like, yeah, that's what engineers do, right? We figure it out. So maybe sometimes that's foolish. I have heard the comments about this sculpture, and there's been many processes. But we start with, she builds these incredible scale models. They're beautiful. They're artworks in themselves. And we start with just photographing them, calculating the areas, like the projected areas. This sculpture is interesting because, as Nancy mentioned, the idea was that it could go anywhere in the world. And So when we check it for a specific site, Texas has basically the wind loads and fatigue loads are the controlling kind of load cases for this sculpture, but they aren't as extreme as what we checked it for. So Nancy, as I was reviewing this, because we did this a while back, I realized that we doubled the amount of boats and we increased the size of this sculpture significantly. And so that allowance that we had initially to go anywhere in the world allowed us to double the amount of boats on the sculpture at this specific site. So this is so you're seeing some of our calculations, and calculations aren't as posh and beautiful as like architecture, as the finished product or artwork. If you go back one slide, I can kind of walk you through this process. But the first thing is like you come up with the area, the projected areas, and we do every side from the two principal sides and then the top and bottom. And then we analyze the sculpture or the steel frame. I come up with a steel frame. Nancy came up with it originally, and then I modeled it with all her angles, and then we adjusted it so it would work structurally. And then kind of what you're seeing on the right side of your screen is kind of the stress diagram. Blue, green means it's very low stress, which is good and what we want. Or that's specifically this case in Austin. So the members are not highly stressed. Tricia, you're gonna do you have questions as you go through? Because I can go
so I'm
through.
curious. So you mentioned that this can be designed. This was designed to be anywhere in the world, and so you wanted to design it for different worst case scenarios for different locations. And typically, maybe if you're designing a building, you go into a building code, you look at a location, and it tells you what the wind load is, the snow load, the maximum considered earthquake load. But you don't have those locations. So how do you determine what is the worst case scenario, deciding to design for the top peak in Aspen versus the town a mile down, maybe?
So what we did the best we could. We're engineers, so nothing's perfect in the engineering world. I hope people know that. It's a little gray. It's not an exact science. So what we tried to do is a really terrible earthquake, something you would see in Chile or Japan, larger magnitude earthquake than you would have here in Los Angeles. And then a hurricane, if it was on the coast, on the Gulf Coast or anywhere else in the world where they had kind of those high winds. We designed it for heavy wind loading and open areas, heaviest wind loading sort of approach. And then we designed it for a kind of a populated town in a place where it gets a lot of snow. And it's funny because when we're doing this, I approach engineering like we're figuring it out as we go. So we're checking everything. We're checking all the limit states. And it's surprising. Like for me, I live in Los Angeles. I design stuff mainly in Southern California. We don't deal a lot with ice and snow loads, but since this cantilever is so much horizontally, the snow load is really a super critical case in other parts of the country, not necessarily in Texas. So did that kind of answer your question? Basically, we do go with the code, the building code, and we kind of picked kind of worst case scenarios around the world that we could imagine where this could be.
Yeah. And I'm thinking too, as someone who uses the building code, and you have a long career of designing buildings, and you've probably designed some complex buildings, but this is by far much more complex than the typical building where we have flat walls and flat floors with loads applied to them. So that process of taking this very complex structure, coupled with maybe a building code that provides some level of or some standards for safety, how do you go from those simplified or more planar type buildings that building code was intended to be used for and apply them to such a complex shape and form that is the structure that has people moving under it that need to be kept safe?
Sure. And part of the whole process is for us to prove to building departments and jurisdictions that this is safe and it's safe to be in the public realm. And the building code is really not intended. This is a unique sculpture or unique structure that is not really covered well by the building code. It's not intended to be covered per se. But there are provisions in the building code. And if you know, basically, if you know the intent of the building code, kind of like when you're doing earthquake analysis, you know the intent of your ductility factors, you understand the intent of failure. Or, when you're doing steel design, you understand the intent of the limit states, and you understand so you kind of track where the failure will be, and you kind of approach the problem like that. And you use the building code, you use the provisions, and you adjust the provisions, and then you defend them. So in your calculations and whatever you present to the local jurisdiction, whether it's in Paris or in Austin, Texas, you argue why this provision in this building code applies to this sculpture, why this structural values or why these, resistance values or these fee factors are appropriate. And, in engineering, you can disagree with me. And that's part of the process is we prove to each other that it's safe. We prove to each other that it's appropriate and that it's reasonable.
And I really appreciate that too, because that shows the importance of really learning the theory and the background, and not just as an engineer. We are not technicians that just blindly go into a set of provisions or standards and follow equations. It really does. That's the art of engineering, is that every situation will be more complex than what might have been envisioned in those building codes. So I'm curious, I see these really cool sketches here that show some about your design process. I even see arrows and lines that remind me of the strut and tie method from some of my graduate concrete classes. So I was wondering if you could talk us through a little bit about your process in designing the different parts of the structure in this piece of art.
So these are both funny images. So that's not my sketch. I do want to emphasize that engineering is a group activity, and you have a team of engineers, drafters who draw up the plans, and you have colleagues and you have engineers that check your work, and you have to prove in your office that it works, and you have to coach your fellow engineers on how to do these things. Yes, you're seeing that strut and tie approach because you can't get Appendix D and ACI to work for this sort of anchorage. It doesn't really apply. And
so this is the foundation that you're showing right here?
This is the pile cap. So these are the anchors for the sculpture down into the concrete base. And then on the right, you're seeing, which is funny, it's the pile that we've analyzed. We've analyzed it separately to come up with those reaction loads that then we applied to this kind of fixed element, because basically the pile, this sits on one single pile that is 9 feet into bedrock, but it goes 23 feet, 24 feet in clay. So we can't use any of the clay layer to resist. Basically, it has no value. So part of the pile analysis was getting it into the bedrock.
So what you're telling me is this beautiful piece of art that cantilevers over this road has an additional 30 or more feet of beautiful art of a foundation that no one can see. I wish that we were able to visualize this.
Well, there's a picture later of the reinforcing for the pile cap. So, and it is interesting. And I love concrete, but it's in the ground here. And we did, I believe we did use a little bit of we took into account the slab helping, and that was, and at that point, we're working with the geotechnical engineer. Again, there's a lot of consultants working on this, and the geotechnical engineer gives you values for the pile that you can use. So we size it, and then we check it for strength, etc.
And I can picture maybe a student at the Cockrell School of Engineering who might be looking at this sculpture and thinking, okay, how can I simplify this down? Maybe they might start with the truss that you had that kind of is the support to all of the boats on top. And you could have a structure, that truss structure with some point loads maybe, and you can analyze it. Maybe do something like that in your statics class. But then we got a short little glimpse of this next slide that actually your modeling looks much more complex than treating these boats as individual point loads or distributed loads. It looks like you've actually modeled the three-dimensional shape and weight distribution of these canoes and boats.
Yeah, so we in our 13-year relationship, me and Nancy have gone, we've been having to deal with jurisdictions around the world. This was done for Paris, but also used for the University of Texas. And I think I did send this to Dean Wood because she was concerned. So we developed this report for Paris because they didn't believe the boats had the structural integrity needed to be safe in this sculpture. And they wanted to do load testing, which would have taken a long time. Engineering is like, we don't have a lot of time and you have to do things within a certain schedule. And on my end, we're usually behind and we're juggling multiple projects. So in this instance, instead of load testing, we did finite element models of the boats, the three typical types of boats that are used in the Paris sculpture, but also in the University of Texas sculpture. And they had concerns with the boats and they had concerns with the wires and the methods of the wires. And so we addressed both concerns and then again argued that the boats are mostly low stress across the board, and where the cables connect, there's stress concentrations, but there's, in a finite element program, you can average over certain areas. So we argue that it's over that area, the stresses are within the capacity of the boat or the capacity of the aluminum. These are aluminum. There's different types of aluminum. So we called the canoe company and got their specific type of aluminum they use versus the John boats versus the, Insta boats that were used. So all of them use different aluminum. We called them, verified. So we called cable companies for the cables and tried to really, and we did research on the cables. There's a ASCE document and that deals specifically with cables and hand tying a cable and the reduction factor for that, so yeah. I mean, we basically research every aspect of it, and then we prove that it works to Dean Wood and others peer reviewing our work.
The joy of having the dean of the College of Engineering, where your art piece is being installed, also being a structural engineer. It's fantastic.
Makes you nervous.
So I'm curious, you mentioned a lot about your back and forth with different design jurisdictions and how they ask questions and you had to revise your design or provide additional justification for them, and your interactions with Nancy, how she kind of creates this initial model. Through all your research and maybe feedback from the jurisdictions, as well as your own feedback from the research you found, how much does the actual design change from the beginning to the end of what you deem is structurally sound?
So this is artwork. So part of my job is or my goal as an engineer is to make sure that Nancy's vision is realized. So it shouldn't change much. And me and Nancy were talking about this, and initially the steel structure that they were talking about, her and her crew and the folks she works with that put this together, typically they wanted 2-inch tube steel or 3-inch max, and as I'm calculating this, I just couldn't make that work. And so I go back and I feel like I'm bringing horrible news, like I failed, right? Like I've done the worst job ever. And I'm like, well, we can use 4-inch tubes. And they're like Nancy's always very accommodating, and she's wonderful to work with. And then I'm like, and we need to add like these reinforcing plates, like 3/4-inch plates on several sides at the base of the truss. And it's starting to look a little rough and and we'll grind all the welds, make sure everything's smooth. And it's interesting. It's an interesting back and forth process, because in this sculpture specifically, we actually, we changed the base plates of the monochrome sculpture, the base plates between the plinth and the sculpture piece. We made them thicker. They went from 1.5 to 2 inches, which is really thick. But the reason is because we weld, the tubes come down, we weld everything, we put stiffener plates, we do all this stuff, and the plate warps. And it doesn't fit well. It doesn't look like Nancy noticed and said, hey, can we fix that? So they fixed it by grinding the steel plates flat. And it's interesting for me too, because I'm like, oh, wow, you can do that. You can actually grind it's fascinating what you learn what a fabricator can do and what a contractor can do. But yeah, it's things like that that the sculpture has evolved at each point, at each project. And we learn, the top connection, the top arm connects to the diagonal support piece, and it's bolted together, and they're two separate pieces so that they ship easily in a crate anywhere in the world. So we have the splice connection there. That connection in a different location, we didn't put weep holes in it. So water puddled. Again, it's not like a specific engineering issue, but water puddled. We basically built a bowl where all the tube steel connects to the steel plate, and water collected there, and the welds, it wasn't as durable per se, and they had to address it at this other site. So here we made sure to put weep holes and ensure that the water drains. So we try to improve as we go along, but that's also engineering. And I appreciate that Nancy is as accommodating as she is with me. Because yeah, I mean, engineering is a process. You learn, and you are doing the best you can. You're checking as much as you can, but there are some unforeseen conditions that will come up.
So just as the piece of art is a living piece of art, so is your engineering. It evolves over time and improves with each site. I'm curious to see some more of the images you've shown. You've talked a little bit about this foundation and the installation of it. And I'm seeing now these perfect drawings. When we draw, everything's nice and straight. That 1.5-inch plate does not warp. And you're learning in the field that things are not as simple as they are just to draw on paper, draw in your CAD software.
Yeah, again, I just want to put this out there. I didn't do any of this. I probably sketched, and my red lines or my markups for the drafter who does this were very ugly, I would say, probably a chicken scratch. So there's talented people that create these drawings based on a team of engineers' input. And specifically, this was also an interesting aspect. You see that vertical line in the middle of that support column? that's kind of a section through the plinth, the stainless steel plates. That is a lightning rod. So that was a specific issue in Texas. They're like, well, how are you addressing lightning? Because there's those thunderstorms and stuff. So what we did was and I hope it works. I'm guessing it works because it's been there. Guessing you've had some thunderstorms, but basically the sculptural piece above with the truss sits on the plinth, and we've isolated the two with neoprene pads between the two plates, the top plate of the plinth and the base plate of the sculpture. So we put neoprene pads, we put neoprene around every bolt, we put it around the washers, which didn't look as pretty, and it was difficult to get the contractor to trim them. They didn't. And but basically, we isolated it and then we ran the lightning rod without touching the plinth down to the grout layer below the base plate. And this is where you have to trust that the contractor actually did this, because I didn't see it with my own eyes, and hopefully an inspector did. But you go through the grout layer and you can see it turn right under the base plate. And I know you can't see me pointing at the picture, but it's the top right picture. And then it goes into a grounding rod that's stuck in the ground. So that was a specific requirement that the University of Texas is like, hey, how did you address this? And we're like this. Nice.
So yeah, I never thought about the lightning load to design for. And you said that there were inspectors look at the process, but I understand you were also there to inspect during the installation that it was built according to your designs and your plans, correct?
Yes. So every state does it a little differently. And in California, or on the West Coast where there's earthquakes and where there's hurricanes, like in Florida, probably the coast of Florida, the codes are very strict, and inspection requirements are super common. Basically, there's an inspector inspecting everything, and the structural engineer is required to go on site and review the critical phases of the structural elements. In Texas, it's a little different. And so, but we required it as part of kind of our typical process. And so I did go to Texas, and I'm from Texas, so it was nice. I actually brought my dad to the site, which you typically don't do, but it was funny because I thought it was going to be easy because it's the foundation. It's super simple. It's a pile cap. You can't really screw it up, right? And so I do my custom, as a structural engineer, you look, and you're not an inspector. And that's super critical, like where there's a distinction between inspection and observation is what we do. It's liability, all that sort of stuff. So I go, and then I look at the rebar, and we had specified these terminators, these headed terminators, instead of bending the bars, because the bars were so huge, so they wouldn't fit in the pile cap if we had 90-degree bends or the rebar was bent. So we had these, so the terminators, they were on there, but none of them were screwed in. So, and the contractor was ready to pour. They're like, are we good to pour? And I'm like, you gotta connect all these. Basically, what was kind of holding the pile cap to the pile below that goes down 30 feet, they didn't finish it, and they were going to pour concrete. So it is, I would say I always find it's super important. Every time I go out to the site, I always find a bunch of stuff. It doesn't make me popular with a contractor. The contractors usually are really annoyed. They like it when engineers go out and they don't see anything and it's all perfect. But I find that you at least have to find something. Otherwise, nothing's perfect. Our drawings aren't perfect. Our engineering's not perfect. Certainly the construction process has the same kind of. That's why you have these QA/QC provisions in the building code. And so I think that's super important.
Well, I'm really glad that you were there to observe so that make sure that the anchors were properly installed and now it's safe, but also so that you could come back to your home state and your alma mater and bring your dad along to show some of the great art that you are helping to design structurally.
Great. Thanks, y'all. We're going to open the conversation up to the rest of the panel. It's really a great moment to transition to talking about the installation and also the many ways in which this artwork does continue to live on, both for us here in Texas and then in the ways that different iterations of Nancy's work have referenced back to this work. So Nancy, do you want to talk a little bit about the installation? And then I'd love for us to have a conversation, including Sharon and Andrée, about how some of these technical aspects of the work might help you reframe the way you interact with it.
The images you're going to see are just snapshots that I took as we were building the piece. And I think these early images, which are the structural aspects of it, I think Jaime could address better than I can. And then as the sculpture starts getting built and the boats start going on, I can carry on with the conversation then. Sure. I think Jaime has more expertise on this than I do.
Yeah, so what you're seeing is they've poured the pile cap, and these are the anchor rods that are cast into the pile cap. That plate right there is a template plate. It'll be removed, and then the base plate and the plinth will be lowered on those bolts. And then the rebar is, when they pour the concrete back, the rebar is there. And there's supposed to be more reinforcing that they'll put around it once the plinth's in place. And then these are the pieces. Again, we've worked with Nancy. She had specific requirements, and you can see the vertical truss piece on the top left, and then you can see the horn-shaped truss piece. This sculpture was like super appropriate for the University of Texas because it looks like a longhorn, which is awesome. Hook 'em horns. But you can see those pieces, they fit. They're smaller, and they were bolted together so that they could fit on a truck, the back of a truck, go cross country, or get in a shipping container and go across the ocean. Here you're seeing the stainless steel plinth. And again, I just followed what Nancy wanted, her improvements from the Paris engineers. And you can see the stiffener plates at the base to transfer the plinth loads to the concrete, to the bolts, basically. So the plate's not doing all the bending alone, because you need thicker plates. And here you see the stiffener plates and the transition between the sculpture and the plinth, and all the stiffener plates. And again, it's like I show Nancy this and say, hey, this is kind of what's required. And it's amazing that she wants to show it in the finished product, because you see all these stiffener plates and bolts. And there you see the longhorn. I think when it went up, I was like, oh, this is perfect for Austin and perfect for the University of Texas. And Nancy, you can probably take over here.
This is the steel structure once it's installed. And I love the root exposure of the steel structure and what Jaime put into designing it. For me, looking at this sculpture, a person gets a kind of crude education in physics and engineering all at once just by looking at this sculpture. And I really love seeing the steel exposed. I keep thinking of the Eiffel Tower when it was first designed, and how people thought that steel structure, that cast iron structure, was ugly. And I love seeing the structure of this as the sculpture grows from it. So you can keep moving through these. It's kind of filmic.
And you can kind of see that the front part has the extra steel plates that are welded on two sides of it. And you're right. You see the physics. That side is taking large compression loads, so those members need to be larger, and the tension loads on the back sides. Steel does really well in tension, so you don't need the extra bulk to take the loading. Those are the neoprene pads that isolate the top plate, the sculpture, and the plinth, and the bolts. So all the bolts, so that the bolts don't take charge. As you can see, the contractor didn't trim them. I think we tried to get them to trim it so you didn't see the neoprene. Ideally, they would have done
that. This is as we're putting on the first bit of the boats, and you can see the very first tees we're putting on. And you can move through these images kind of filmically. Yes, you can. That's as we're putting on the first tees. We're just kind of moving through these. Now we're starting to put on tees in the front part. And what we do with the boats is we kind of nestle them into the crevices of the sculpture, and then we build more crevices and continue nestling each boat as we put into these crevices. More tees, we're building out. This is as the boats are going on. This is a little filmic. You can go a little quicker. You see a boat being lowered and it's going lower, another image, yes. And then it goes down into the sculpture. The crew receives it and they cable it in, and then they drink some water. And the crew is tied into this steel structure, and they can climb around that great thing as it's a great climbing thing for them when they're building it. And I think that's all of the construction images that we have.
So I want to thank you for sharing the construction images. I was on campus when this was built, but because of the fences, I never got to see that. And so I find it absolutely fascinating. I agreed completely with Jaime that this is a perfect sculpture for UT Austin. I absolutely love it. I guess one of the questions I had was the balancing of the load seems to be so difficult, because as you're adding more weight, you've got this tensegrity structure going on. So Jaime, were you also involved with calculating construction loads?
We do. So you check it. I think what we find is that there's the completed loads, and you're right, there's the unbalance, but the sculpture is fairly stiff and stout. And, the fact that we've checked it for several feet of snow on this cantilever or these large wind loads, the sculpture, as far as construction loading and the unbalanced loading, it isn't that significant. So it's not, it wasn't a critical load case, I would say.
But seeing the construction workers almost like a jungle gym climbing around it made me think that there could be considerable loads. But I guess if you've designed it for really high snow loads, you've already got a lot of additional weight on the sculpture.
Yeah, for me, I would be more concerned about probably the boats and like if a boat wasn't fully secured. Right. And the wires. But to be honest, they kind of, that's part of the artwork, and that's part of Nancy's crew. And they have a lot of, maybe Nancy, you can speak to this. They have a lot of experience building these things. So it's almost like a craft, and it's like a welder for a steel structure. Like they're walking on those beams and doing those full joint penetration welds in the middle of the air. And there's an art to being able to know what's safe. And they are tied off. They're as tied off as they can be, but you're right. I mean, it's, Nancy, maybe you can chime in, because they've practiced this, I think. And they're super safe.
I think what Jaime is saying is correct. My crew is super proud of the quality and the safety, the quality of the work and the safety they abide by in making the work. And every time a cable is put on, another cable goes to another structural situation to continue that load. So it's no one cable anywhere on a boat. If you look at the sculpture, you'll see that when there's one boat to one cable from the another direction, the cable is pulling it the other way. So far, I mean, all of these sculptures require maintenance of a certain kind. They need inspection and they need to be cleaned. And if there are cables let loose, or if there is an aluminum boat that is losing its strength in some place that the boat is tied, it needs to be attended to. But so far, this piece has been there only 5 years now, 5 or 6 years, I believe, not quite 6. But, you know, I have a lot of sculptures all over the world and there have not been any issues yet. So touch wood.
And Nancy, does your team do the inspections, or do you have a standard inspector who goes out?
It depends upon the situation. The piece that we built that was 95-foot cantilever over the spaghetti bowl of roads, we were inspected every cable, every bolt, every single thing. We were watched like hawks, because it looks so discombobulated to that community and in the situation we were in. My own crew, they watch over each other's shoulders, and they are like a team of longtime pals, and they are really check each other's work and recheck it. So if an inspector is necessary, an inspector will come out. If an inspector is not necessary, we inspect ourselves, because it serves everyone for this thing to be structurally sound.
Just so you know, like, our drawings require inspections, but it really is up to the jurisdiction to actually, and the contractor to implement them.
I have a safety follow-up question. So watching people behave around this sculpture, it's not uncommon that you'll see people approach it and then walk to the opposite side of the street to go around it. They don't want to go underneath it. It just looks, it looks a little threatening, right? And I often assure people with information that I was told at the time that we installed the piece, which was that the Norman Hackerman building, the beautiful building behind it, was rated to withstand 90-mile-an-hour winds, but this sculpture was rated to withstand 175-mile-an-hour winds. So this just seems like a great opportunity to ask, is that legitimate information?
I would have to check on the 175 load case.
Okay.
I think you should just say that it is designed for higher wind loading, and also an interpretation of the code that's a bit more stringent. So we applied wind load simultaneously, vertically and horizontally, which isn't necessarily required. But then when you're reading the wind sections of the building code, it doesn't really address this sort of sculpture. You would have to, again, do maybe a wind tunnel test, but even a wind tunnel test, since these evolve so much, wouldn't necessarily be, could or could not be helpful, but then the budgets doesn't work. So it's engineering, and we've done it. I think we've proved that it works in most situations. It's, you could say it's designed for hurricane level wind loading, and in Austin you don't get that. So most of the buildings aren't designed for that. So so that's something.
I'll stick with that language. That sounds good.
And then plus I'm an engineer, so I'm always like, there's always a lot of factors and liabilities that you have to work into your drawings and your plans, and that's just part of the process.
With this being near the engineering quarter of the university, I would be curious to see how many of those people who either walk close to the sculpture or far away from the sculpture are those who are the engineering students who have a little bit more faith in the structural engineering that went into the design.
By the way, I do not alter my path. I go straight down. So I have full faith in you, Jamie.
Yep. It's that UT education. Like,
that's right.
Totally.
So speaking of a UT education, we have some really great questions that students and folks from the public have posed while we've been talking. One of them is asking about the materials, Nancy, that you choose for your objects. Wondering, how do you choose the materials, boats and other objects? And specifically, how did you choose these objects for this site at the University of Texas?
I started working with boats specifically, I think in 2006. And my husband had a canoe, a Grumman canoe. And I remember looking at it one day, and I remember saying to him, gee, these things look just like my airplane parts, because I had been working with a lot of airplane parts at that time. And he looks at me and says, silly, it was made by Grumman. Grumman. I go, oh yeah, Grumman, airplanes, boats, design, the rivets, the aluminum. And when the canoes started becoming more popular right after World War II, when this engineer, so I thought, those boats are beautiful. And I love the abstract form of them. I love the figurative nature of them. I love the surface of them. I love finding them from these people in Northern California on the Russian River who have different rental places. And one part of the river is very rocky and one part of the river is deeper. And one of the boats gets beat up more than the other, and there's welds in it. And you see all the bumps from the rocks and the experience and the life that the boat lived through and had. So I love that about these pieces. And I love the patina on them when it's raining and when the sun is out. And over time, it seems like the surface is always changing in the different light. So I hope that answers your question.
Thanks, Nancy. So the next question we had relates back to what y'all were talking about earlier with the inspection. And I think we can think about this on more of this question on a larger scale too. Is there an estimated lifetime of this art piece due to the rigging, tuning, and corrosion? And then also I might add to that question, in relation to being an artwork that's on a university campus, if Andrée or Sharon, you wanted to share some perspective on artworks on campus too.
So Nancy
okay.
So Nancy told me it needs to last 40 years. So, or basically it's, and that ties in kind of to the fatigue loading that we've checked, the cycles that we've checked. But so that's kind of our metric, which is a typical building lifetime amount, about 40 years. We realize that buildings will last, like they get to the end of their useful life and then they go another 100 years or are retrofit and adapted for another 40 years. I believe that this, based on the engineering calculations approach, that it can last a long time. I won't say how long, but more than 40 years. I also do believe that it is artwork, and all artwork needs to be conserved, just like a building needs to be maintained. You have to put new roofing on buildings. You have to make sure their facades are watertight and airtight. And there's a lot of things that you do to maintain a building. And you have building engineers. You also have art conservators that do need to maintain this sculpture. And we have the drawings and calculations for future generations to look at. And but like the cables, like Nancy was saying, these, in 20 years or on a regular basis, this should be inspected and preserved and cleaned, and the wires, the cables should be inspected, and if there's any loose cables, they should be replaced. But part of that maintenance, I think, will help this artwork last probably longer than the buildings.
Right. I'll jump in a little bit here. I think it's not uncommon at UT for contemporary buildings to have an expected 30-year lifespan. And the works that we acquire in our collection, we expect to far, far outlive that. I mean, we expect them to be around for generations to come. We have a really robust conservation program that not only has a team of conservators, but also student volunteers that help us monitor the works and help us maintain them. This piece in particular, I know we have it power washed 3 to 4 times a week. I mean, a year, sorry, about 2 or 3 times a year, I think, periodically. And the person who oversees that work, you might remember Nisa Barger, who is the project manager on this. She has she maintains a 20-year conservation program for each work in our collection. And so she knows when it's time for there to be inspections or when there's time for a power washing. And so as long as we follow our plan, I expect this should be around, as I said, for many generations to come.
Thank you. Jaime, this is a pretty specific question that I think is probably best for you to answer. Were the canoes themselves adequate structurally to simply be tied to the primary armature, or did they have to be reinforced somehow prior to installation?
They are typically, because there's so many connection points along the boat, we've checked the aluminum and the local kind of limit states of the holes that Nancy's crew punches into the boats. So we check all the, tearing limit states, etc., failure states associated with those connections. We do have them we do try when boats overlap, we ask to be bolted, and that kind of doubles up that connection, makes it a double shear connection. And we've checked the aluminum boats and we've checked them locally, and we have suggested at times reinforcing them with an additional plate, but we also realize that that's impractical. So the boats are sufficient, and as we've looked at these, there's not buckling failures, and I do feel like the shape of the boat is helpful as far as kind of those kind of local limit states and stresses. But in our studies of the boat specifically, we had those point loads, and we saw that the stresses under like high wind and snow and all the different load cases, that those stresses were fairly restricted in area, and that the boat is pretty redundant in that area. So we checked buckling and also just the strength in those areas where the connections hit. Those are the critical spots on the boat. So yes, from an engineering perspective, we try to check everything we can. And then there's the other part is like, we have to let the artists do what they do. And so my job is to prove that it's possible, that it's good, that it's reasonable. And I think that's how our calculations are. They're like how I'm talking. They're a rambling explanation of proofs. And 1, to prove to myself that they work, and then 2, to prove to someone else like yourself asking these questions, because we've been put on the spot about this before.
Great. That relates to the next question. For this particular piece, were there any major compromises that had to be made to bring the sculpture to life, such as changing the positions of the canoes or different materials after considering the engineering constraints?
No,
No. Quick one. Great. And then I want to close out with one last question that I think is really beautiful to tie together the conversation that we had today with the larger context of this piece and the impact that it has on UT's campus. How did you develop this unique concept and design of the piece? Do you have any specific inspirations? You talked about a few, Nancy, but was this beautiful dialogue between art and engineering part of or the main message for the piece?
I think it's a message that became very apparent at the University of Texas because the engineering department is right across the street. And it's a way of building that comes quite naturally to me. And I'm delighted that I've made a relationship with Jaime over the years so that we could work collaboratively on these projects. But the structure and the size and the nature of the work has really kind of comes naturally to me and has been one development after another over time. So it didn't come all at once. It's been kind of a gradual growth.
That's really beautiful. I think that's that also reflects the ways in which this artwork has been integrated into our university campus as a literal landmark for students, also as an artwork that inspires young people who come to visit campus for our Women in Engineering program. They have a program called Girl Day. We saw a slide earlier of some young folks making their own cantilevers. And this work will continue to be integrated into our campus. Thank you everyone for joining us today. Thank you very much to our panelists for sharing your insight and expertise. If anyone has additional questions or feedback, please feel free to stay active on the chat. I will continue to monitor it or reach out to us directly. Thank you everyone. Have a great night.
Thank you.
Thank you.
Thank you. Hook 'em horns.